Welcome to the online lecture for Introduction to Advanced Statistics, and we're basically going to be talking about what is the common themes or common issues across a broad group of statistics. And as we're moving into multivariate statistics or advanced statistics, again, I want you to really remember that we're still starting with the same concepts. We're still looking at kind of the same relationships as we did with the most simple of statistics, including the z-score for single samples, the t-test for single samples, t-tests, and correlations. That when you dig through it all, the mathematics that are involved, the concepts that are involved, and what we're comparing really doesn't change. It's just we're adding layers of that onion. We're adding more and more complexity to what we can do, and generally that complexity is through additional variables, both independent variables, IVs, so the variables that we're anticipating actually impact or predict or are related to outcome variables that we care about, and those outcome variables, of course, are dependent variables. Now, what mainly defined last semester was that we were looking at univariate parametric statistics. And univariate simply refers to not the total number of variates, not one variable, but that the outcome is focused on a single outcome, a single variable, and that's univariate. And then likewise, parametric. And parametric basically just is referring to that outcome, that single DV, that univariate dependent variable, that univariate outcome, was a continuous or ratio data. So it was numerical data where the numbers have meaning. The higher the number is, it means more or less depending on how you define it, but it has a meaning, and that approximately there's equal distance between each one of those numbers. As we're moving into quote-unquote advanced statistics or multivariate statistics, what we're looking at with multivariate, of course, is now there's more than one outcome that we're trying to incorporate in one omnibus test. And again, remember the concept of an omnibus test simply means that the first thing we're doing is we're basically allowing for the fact that we have multiple relationships that are being looked at with a single analysis. And that p-value, that chance that there is or is not systematic difference within that data, is for the entirety of the data. So we're basically trying to get around the problem of inflating our alphas or inflating our chances of error by running multiple single tests, by running one omnibus test. And if that omnibus test is significant, that basically gives us license to start digging into the onion. And obviously the more variables we have, the more layers of the onion. But at the heart of all of this process is, again, that onion eventually gets back down to very simple concepts such as z-scores, such as effect on the top of the equation, all other variance or error on the bottom of the equation, and we're going to see that over and over again, that at the end of the day, when we get to the core of that onion, we're looking at fairly simple comparisons, statistically speaking. Also in this class, we're going to be talking about non-parametric statistics, and that's when our outcome is no longer a continuous or ratio data, it's interval data, or more commonly, categorical data. And again, there's just different assumptions when we're using those kind of tests, and those tests also tend to be a little less powerful, so we have to be very careful in how we're setting up the studies when we use them. So as we've started on this slide, I just really wanted to remind you again what a z-score is. The z-score itself is a way to standardize every single score in your study to the same metric. So if you're using multiple outcomes that are measured on different scales, one scale is a 1 to 10 scale, one's a 1 to 5 scale, one's a 1 to 100 scale, you've got various independent variables, again, on different scales, it would make actually interpretation statistically and mathematically very difficult if we left them all in that case. So behind the scenes of most of our statistics, almost all of our scores are going to be being converted to z-scores as a part of the math. And again, the reason we like the z-score is not only does it put everything on the same metric, it also gives us information because that metric is standard deviation units. And as long as we have a normal distribution, we can make a lot of assumptions then about any piece of data that we have. So if we, for example, know that a z-score of a particular score is a 1, we know that person is one standard deviation over the mean of the total sample of all of the people that answered that question. And that also gives us some information, and again, that common metric. And because we use these z-scores, because we're looking at mean differences, again, at the center of that onion, that's also why that normal distribution is still going to be very important no matter how advanced the analysis is. So again, just a reminder, what we're still doing what is basically considered inferential statistics. So even though we're looking at much more advanced statistical techniques, the statistical techniques we are looking at are still generally considered to be inferential. And inferential usually is determined by it's giving us both a metric of the effect size, and it's giving us the probability that that effect size is due to systematic, meaningful, or, put big air quotes on this, causal differences. So we're inferring that from this sample that we took, from this data that we collected, that if we find a statistically significant effect, the effect is large enough for us to say we're fairly certain this did not occur to chance, we're inferring that means something, that that has information that we can use to apply it to different situations to help us make decision making, whether that's a clinical diagnosis, whether that's determining the future treatment of a patient, or whether that's determining whether or not a particular intervention within an organization is successful or not. And again, as we look at these more advanced statistics, we're going to see that there's a lot more layers of that onion, a lot more complexity, that the omnibus tests become layered on top of each other. So for example, if we have multiple independent variables and multiple dependent variables, and our initial multivariate test says there is systematic difference, it's significant, that omnibus test was supported. Next, we have probably more omnibus tests. So was there an omnibus significant effect of all of those independent variables on one of those DVs? And if there was, then which ones of them were significant? And once we look at those, if the ones that were significant were interactions, we may also then have to explore the nature of the interaction. If one of those independent variables was a categorical variable with 3 levels, we may have to do post hoc tests. So again, we're just peeling away those levels of the onion. And I really think it's important to keep that in mind, that we're not looking at brand new techniques, we're simply adding layers. And I think that's the way to kind of keep it simple and just keep thinking of it as what are the layers I need to move through in this analysis to get to the answers I'm wanting. So again, like all inferential statistics, the equations, no matter how complex they look if we ever wrote them out, are basically just, again, we have the variance of the effect, the mean differences or the covariation, depending on what our independent variables and dependent variables are, on the top of the equation, and on the bottom is all unexplained variance, all error variance. And that's really what we're looking for. Does the effect basically outweigh the noise of everything else going on? So again, this is an introduction to advanced statistics, and I know last week we basically reviewed what we learned last semester. This week we're basically kind of doing a broad overview of what we're going to cover this semester. So again, we're going to be talking about multivariate statistics, and multivariate simply again refers to the number of independent or dependent variables. We're going to talk about some other advanced statistical techniques, and when I say this, I'm not sure advanced is the right word. It's more that they have a more unique set of assumptions and methodological issues that it's hard to lump them into the parametric statistics that we covered last semester. Of course, some of the overarching concepts that we're going to hopefully be covering in this class is how do you select the right statistics. We're always going to be coming back to reviewing the basics because underneath the complexity of each one of these statistics is those basics. And one of those basics we're going to really talk about today is the importance of continuing to assess our distributions to make sure they meet the assumptions of the test. So again, we're going to be reassessing multiple regression, looking at it in more complexity, and truly hopefully understanding how to master it. We're going to be looking at multivariate analysis, so different techniques that allow us to actually look at multiple dependent variables, multiple outcomes. Now, we're not going to cover all of them. There's a lot of techniques. There's a reason that you can get a PhD just in statistical methodology, because a lot of the things we're going to touch on can be their own class. But we're going to look at some of the more commonly used and more commonly understood multivariate statistics. And finally, we're going to tackle some of the non-parametric statistics. So some of them were interesting techniques we can use, and I really chose the ones that are more applied in their use. So helping us categorize a large amount of data to hopefully make decisions, whether that is higher or not higher, whether that is provide a treatment or not provide a treatment. And those are non-parametric statistics because those are categorical outcomes. So hopefully we're going to add all 3 of those to our toolbox, and let's kind of talk a little bit more now about the types of multivariate statistics that are out there. So multivariate statistics include more than one dependent variable in the overall omnibus analysis. That's pretty straightforward, and there's that definition. And I've kind of already covered this in the previous slides, but there it is in print. So the types of multivariate statistics that we're going to cover, we're really going to focus a lot on pretty much the most commonly used one, which is the MANOVA or MANCOVA. So this is simply adding another layer to the ANCOVA or ANOVA onion. So multivariate analysis basically refers to we're still using the ANOVA, and in fact when we run a MANOVA, all we've done is we've taken an ANOVA and we've added additional outcomes, additional dependent variables. And if that omnibus test is significant, we're going to basically just walk through the onions layers through the rest of the ANOVA, depending on, again, what our independent variables are. And again, MANCOVA is simply also having covariates involved. We're going to talk a little bit about canonical correlation regression. And again, this is a way to actually use regression to predict multiple outcomes. We're definitely going to be looking at principal, component, or factor analysis. And generally, this is kind of in its own category. What this is most commonly used for is to actually identify clusters of variables. So it's a little bit of a different use. We're not necessarily trying to use a bunch of independent variables to predict an outcome variable. We're actually looking at all variables equally to look to see how they cluster together. And this is usually used in some form of validation of a multi-item measure. But we're also at least going to touch on how you could actually use this again as an inferential statistic. We're going to touch on structural equation modeling. And again, this is beyond the complexity of this one class, but I'm definitely wanting to at least spend a day on this so you have some understanding, because you will run into research articles that use structural equation modeling. And generally, again, what structural equation modeling is it kind of combines principal component analysis and multiple regression. So it's at the same time looking for clusters of independent variables or variables that seem to be measuring similar constructs, but then goes a further step and then asks how are those constructs interrelated to each other. So I've got a little model here at the bottom of the page. So for example, our structural equation model might simultaneously determine that 3 of those boxes at the top are 3 items that cluster together very well and seem to be measuring the construct of cognitive ability. Meanwhile, to the far right, there are 3 items, again the boxes, which seem to be measuring achievement. And we're then going to be looking at, does cognitive ability have a significant relationship with achievement? And of course then family, background, adjustment, and maybe even individual variables that have some relation. So this is allowing us to do, again, a fairly complex analysis where we're both asking the question, are our multiple items that we're using to measure a construct truly measuring something, hopefully that construct, and then also once that construct is identified, is it interrelated inferentially with other variables? We're also going to look at least briefly at contingency tables, multi-wave frequency analysis, and what this really means is very complex chi-squares. So just broadly, remember the chi-square is a technique where we're using categorical variables to predict or infer other categorical variables. In other words, it's a technique we use when we have both IVs and DVs that are both categorical. The problem with those is there's only so much and so many variables you can do using just chi-square. Multi-wave frequency analysis, the way it was described to me in grad school, is basically chi-square on crack. It allows us to compare an enormous number of categorical variables in multiple combinations to each other. Now again, it's a fairly advanced technique, but we're at least going to touch on it so that if you run into it, because we do occasionally see such analyses in applied articles. Of course, we're going to come back to multiple regression. And again, as we talked about last semester, there's a lot more we can do with it. I often like to refer to it myself, and I often think of it this way. It's the kind of kitchen sink of advanced statistics because we can make it do almost anything. Now, we do want to make sure that if we're making it do something, it's because no other statistical technique will work. So if you have variables that will allow you to do a MANOVA, don't run a multiple regression. You've got a more refined technique. And it's not just about being simple for simple's sake. When you have an existing statistical technique that can be used in lieu of multiple regression, the reason it was designed was to be a more accurate and more powerful way to analyze that particular types of data. So when we go to multiple regression, unless all of the variables are continuous, which is what it's actually designed for, if we're using it to kind of try to force in dichotomous variables or break apart categorical variables into multiple dummy-coded variables. If we're doing any of those things, we want to first ask, is there a technique that would let us do this without these steps? Because when we use those steps, though we can do it in multiple regression, it often results in a less powerful analysis. Now, there's a whole bunch of other advanced statistical techniques out there that we're at least going to touch on briefly. Time series analysis allows us to basically use time as one of our predictors, but not just once or twice, but a whole bunch of times. Survival analysis is another example of this, where we have a study set up, usually with multiple predictors, maybe multiple outcomes, but also we're testing our subjects time after time after time after time. Time series usually refers to any type of analysis where we're looking for long-term trends. So, for example, does a particular intervention slowly peter out, continue to provide positive effects strongly at the start, but then they peter out, doesn't work very well at the start, but then becomes very powerful later on? Those are questions that often would not be answered by a single analysis. And that's a good area where we could use a time series analysis to get a more refined understanding. Survival analysis is used more oftenly, kind of morbidly, in the medical profession. So when there is a terminal disease or a disease that's known to have a very high mortality rate, when an intervention comes in, does it increase the survival or the length of survival? It can be used, however, out of the medical events. In fact, a lot of organizations use survival analysis, specifically looking to see how long someone takes to leave an organization. Mixed effects modeling basically is just kind of a broad catch-all term for when we're kind of trying to create multiple between subjects and within subjects designs across a very complex set of predictors and outcomes. A lot of times we'll see mixed effects modeling where we actually go into a MANOVA or an ANOVA and basically tell it what to look for. What variables are we actually interested in, what ones aren't? And usually when you're using mixed effects modeling, what we're trying to do is to create a more refined model within an existing system. We're basically telling it, for instance, don't look at these interactions. I don't want you to waste power on them because I don't expect them to be significant. And like anything where we go into a statistic and start to take control, we want to make sure we have good methodological reasons to do so and often good reasons from the literature to do so. Another one of those is hierarchical linear modeling, and again, this is a way to go into multiple regression and kind of select what we're wanting to do. And finally, we're going to look at categorical data analysis, and we're going to look at a couple of these techniques that are often used in applied settings and really get some mastery of them, including logistic and ordinal logistic regression. And what we're looking at there is the outcome is either a categorical dependent variable or a dichotomous continuous variable. We'll touch on Poisson regression and profile analysis. Again, both of these are techniques that you might run across in research articles, but are a little more complex than what we can cover in a semester. And we're also going to look at discriminant function analysis, a great little technique where we can use a bunch of predictors to kind of predict what group or category people should end up in. And we'll talk about that later in the semester as well. So again, we're going to always be thinking about, as we go through these advanced statistics, when would we use them? Now, as we get more complex, as there's more layers of the onion, it's going to become a lot harder to try to just graph out kind of a decision tree. But I want you to continue to keep in mind, what are the types of data that this particular statistic technique uses? What do the independent variables have to look like? What do the dependent variables have to look like? Also, how many independent variables and dependent variables are involved? And of course, always, is the design between subjects, independent measures, or within subjects, or a combination, a mixed method? So just a quick example here, if your DVs are all categorical and your IVs are all continuous, that's logistic regression. So logistic regression is really good at having a whole bunch of continuous predictors predicting a categorical outcome. If both your independent variables and DVs are categorical, pretty much you're at chi-square. And again, we kind of talked about some of the more advanced techniques like multi-wave frequency analysis. If our IV is categorical and our DVs are continuous, we're at t-tests, ANOVAs, MANOVAs, etc. And again, if our DVs are continuous and our IVs are continuous, we're looking at correlation, multiple regression, possibly structural equation modeling. So again, just a review of the basics. Types of studies go from everything from descriptive to inferential. Usually correlational is thrown in there in kind of the midpoint, but that really is just a description of what is our point. Are we looking to just describe what's happening? Are we looking for just basic relationships, but we're not trying to claim they're causal? Or are we actually trying to infer a meaningful predictive difference from our population of our sample to the population we're actually trying to infer to. And that's the difference between that correlation versus causal. We're also wanting to remember that the types of studies can be parametric, the outcomes are continuous, or non-parametric, the outcomes are categorical. And finally, as I just continuously want to drum in, we want to be very careful when we use the word cause with inference. We can talk about inference without cause. If we're talking about causal inference, we're inferring a cause, we have to make sure the study itself, regardless of the statistics we used, was set up to determine causal inference. And again, that's Mills' canons. The variables have to covary, so there has to be that statistical relationship, but that's just step one. You have to establish within your methodology that whatever your predictors are, whatever your independent variables are, your methodology made it clear they preceded the effect. They're not co-occurring. They're happening first because you have control of them. You caused them to happen or not. And finally, your study has to rule out any alternative explanations for why you would find that account. You have to hold all other variables basically static. And again, a review of the basics on hypothesis testing. I just want you to keep in mind, again, that idea that what we're looking for, our statistics are set to find the null hypothesis. Our statistics are built around the idea that when we run a statistical test, 95% of the time, if the effects are just random, we're going to reject our hypotheses. We're going to support the null hypotheses. And what we're looking for is the alternative hypotheses. And we only accept that alternative hypotheses if there is strong evidence that it exists. And how do we find that strong evidence? Again, with power. And things that are influence power, the likelihood to find a statistically significant effect in patterns of data is the sample size. So the more people we have, the more likely we can be confident of smaller effects. The effect size, so the stronger the effect, the more likely we are to find it. Type 1 error, alpha, so we could always accept a lower alpha. In other words, I'm going to basically make a claim of effect even if there's a 10% chance I'm wrong. Generally, in our field at least, this is rarely allowed. The one-tailed versus two-tailed test, and again, the idea here is that if you focus all of your statistical power on a directional hypothesis, you have more power to find an effect than if you're just kind of flailing around looking for any difference. And that's one of the reasons it's often a good idea. And most of our statistics, by the way, are preset and assume a one-tailed significant test. So when we run an ANOVA, for instance, we're running a one-tailed test. And we want to make very clear then that it's our responsibility to make sure we have those directional hypotheses to set that assumption. And finally, between within versus within subjects. So between subjects, we know there's error differences between the people in our various groups, and we have to adjust for that, which means it's less powerful. When we have a within subjects test, we know they're the exact same people. We don't have to statistically adjust for individual differences because there shouldn't be individual differences. So again, if you can do a within subjects design, you'll usually have a more powerful design. It's more likely to find statistical significance. So, since at the end of the day, no matter how complex the test is, we are basically just getting down to the bare levels of that onion, we still need to be assessing the distributions of any continuous variables. So parametric tests make an assumption about the shape or parameter of our population distributions. And that's focused on the amount of variance, the possibility of skewness, and the possibility of kurtosis. So types of parametric tests again include all regressions, all ANOVAs, all MANOVAs, all multiple regressions. So each test has a different set of assumptions, but they all assume that the outcomes, the IVs, those continuous variables that we are looking at the end, are normally distributed. They don't suffer from excessive skewness, they don't suffer from excessive kurtosis, and if there's multiples of them, that they are varying similarly to each other. These assumptions must be met for valid results, and we have to test the assumptions on sample data. Now, the sample data concept is basically when we have an enormous data set. Sometimes we'll take subsets to test this, but generally speaking, what we're going to do is simply run the tests on our sample data, the data we've collected. And there's various ways to test these assumptions. So common parametric statistical assumptions include that the data is normally distributed. So we test for skewness, we test for kurtosis, and we look for outliers. And we're going to talk about, again, how we do that in a moment. we're going to make sure the group variances are homogeneous in categorical IVs. So this means that if one of our predictors, one of our IVs, is categorical, we also want to check not only is the overall outcome, let's say anxiety, is not skewed, doesn't have outliers, and doesn't suffer from kurtosis, we also want to make sure that the variance of that variable, again our outcome, in this case anxiety, looks similar for the different levels of our predictor variable. Now, that is what we're looking at for the categorical IV, because with a categorical IV, we'll have a distribution of data for each category within that IV. If the IV is continuous, we want to look for homoscedasticity. And again, that is that the relationship, the correlation, the linear relationship between our predictor, continuous IV, and our outcome, continuous IV, is similar at different levels. And we'll go into this a little bit more in detail, and we did last semester, but also in this lecture. Again, if we have continuous data, we're assuming that the relationships are linear. We're assuming the residual errors are randomly distributed, and this is kind of a complex concept, but the basic idea here is that we know that there's random noise in our data. What we're looking for is, again, is that random noise more common or less common at different levels or in different categories? If so, we violated an assumption. In other words, the error noise, the variance that isn't explained, should be fairly similar at 3 different categorical levels for us to be able to make the assumption that that error is not also systematically varying with that categorical variable. If the error is also varying, in other words, we have a lot of error in our first category and no error in our second category, that tells us there's something more going on than just the relationship between our IV and our DV. And that also means that something is not being captured by our statistical test. We violated an assumption. We also want to test if the missing data is either completely at random or at least random, and I'll talk a little bit about more of that in this lecture. And finally, of course, we want to make sure that if we've got measures, in other words, multiple items that are being collapsed into a single score, that that measure is reliable and valid. It measures what we think it's measuring, and it measures it fairly reliably. So measuring normality and assessing distributions. So with skewness is basically a function of n. So the equation is actually the square root of n, the size of your sample, divided by 6. So you can kind of see that the larger the sample, the more tolerant we are of skewness. It becomes a smaller issue. So positive skew versus negative skew, what we're literally going to be doing is calculating the skew of our distribution, and what we want to ask is it within a range of either positive or negative 2 times the SES? So that kind of gives us that information of what's going on, and it's our metric to determine if we violated or not violated skewness in an outcome variable. We also want to look for outliers. We may actually find that if we find that we violated skewness, a lot of times what's causing that violation is 1 or 2 extreme scores. So an outlier is a score that exceeds 3 standard deviations from the mean. So for example, test scores that exceeded 3.29 standard deviations, for example, would be violations. So I've got an example just right down here, and we can use z-scores to calculate this, but at the end of the day, whatever your mean and standard deviation of your distribution is, multiply the standard deviation by 3, and then add and subtract that from the mean. If you have any scores that fall outside of that range, that may be causing your problem with skewness. Now, once you find an outlier, you need to ask, is that outlier a legitimate part of the population, or is it something that you can safely remove to get rid of your problem with skewness to continue forward with your analysis? And just again, as always a reminder that anytime you do any adjustment to your data, make sure that you include it in your methods and your results section that this is what you've done. So with measuring distributions, we also want to look for kurtosis. Standard error of kurtosis, in this case the SEK, again is the square root of n divided by 24. And once again, we're looking for any score that is calculated for your outcome variable, your IV, where the kurtosis is above or below 2 times the SEK. And again, if we find that it is below -2 times the SEK, it's a platykurtic distribution, it's a flat distribution. And if it's above 2 times the SEK, it is a leptokurtic distribution. It's a very tall distribution. And what we're really looking for here is, this is step A. Generally speaking, what this tells us is that the distribution is not occurring in a way that makes a lot of sense for how our analysis looks at it. And it's also the precursor for us to determine, is there differences in the distributions between different categories? Again, IVs that are predicting outcomes in our DV. Just a quick way that I've always remembered these terms is lepus is Greek for rabbit, so leptokurtic distributions, which are tall, remind me of a rabbit, and platykurtic reminds me of a platypus, which of course is a very flat animal. So when we're assessing distributions above and beyond this, now what we're looking for is the homogeneity of group variance. And the ways we can look at this, we've looked at in the past in Levine's test. As we look at more advanced statistical techniques, another one we'll be using is the Hartley F-max test. And again, it's calculating the ratio between the largest and smallest group variances. In other words, the differences. And what we're hoping to find is that when we take that outcome variable, that IV, and we break it up into its individual subgroups because of a categorical predictor variable, we find very similar distributions. We want to find differences, but we want those differences to be in the averages, the means, x1, x2, and x3. What we're not hoping to see is that also the distributions vastly changed. And both the Hartley's F-max and the Levine's test specifically look for this. They're looking for that difference. They're looking for something like this, where yes, the mean differences are the exact same between these two examples. x1, x2, and x3 are the same distance apart. And our statistics, if we didn't check for the assumptions, would give us the exact same results in these two cases. They would both tell us how big the differences are and give us an effect size. But in case one, we can trust that. We actually can trust that all that really is going on is the distributions are shifting based on the impact of our three categories. In the second example, there's more going on our statistics did not tell us about. That in the first category, not only did they get the lowest score, the people in that category didn't have a lot of variance. They pretty much all scored very similarly. And though group 3 had the highest score, some of them scored almost as low as the mean of the second group. So again, more is going on that's not being captured by our statistical test. That's why we need to test these assumptions. Because if we haven't tested the assumptions, we may be missing something important. That doesn't mean that this isn't necessarily an important discovery. It's something, though, that would not be tested by the old omnibus test of what we're currently looking at. If your IVs and DVs are continuous, what we're going to now look at is homoscedasticity. And again, it's a very similar concept. We're looking to see if the statistical variance is similar across our study. What we're looking for is homoscedasticity. And what this basically refers to is the reliability of a measure can be assessed with common standardized tests. And in that method, basically, low scores on both measures are about equally distributed as medium scores on both measures as high scores on both measures. In other words, the amount of error around our predicted linear relationship is roughly equal throughout the process. What we don't want is heteroscedasticity. Heteroscedasticity means, for example, you can very much see, you're going to visually be able to see a fan pattern here. There's very little differences or error at the start of the relationship. So when you're low on both your IV and your DV. But by the time you get to high scores on your IV and DV, there's a lot of variance. Now you can assess this either by eyeball, by looking at scatter plots, or again, we have the multivariate analysis of Bartlett's test to allow this. So again, we want homoscedasticity, we do not want heteroscedasticity. And again, it's not necessarily that heteroscedasticity is just bad. It means something else is going on that our statistics would miss. And that if we make the conclusion that there's a linear relationship there with no error, that it's a trustable measure, we're basically turning our back on the truth that there was something else going on in our data that we're not accounting for. Final thing I really want to focus on is the idea of data missing. So assessing distributions, looking for any data missing. And generally what we're talking about with data missing, it might be a participant that only filled out half of the surveys. It might be someone that missed a single item. It can also be someone that basically provided very little information, just enough for them to be in your data set, but none of the outcomes are DVs. Since we have some data on these people that are missing some of their scores, we do want to examine why we're missing those scores. And what we're hoping for is data missing completely at random, that there is no systematic pattern in the missing data. Data are missing for reasons that are not relevant to any of the variables being studied. Missing data is due to some random error and is independent of observations and unobserved variables. Now notice that one right there I want to focus on. missing due to random error and is independent of observed variables, well, we can test for that, and unobserved variables. We can't. We can't test for unobserved variables. We didn't observe them. So we often assess this through correlation. We look for correlations. For example, we can create a missing versus not missing categorical variable and then look for correlations with our outcomes, those outcomes that were missing variables, to see is there a systematic difference. If we find that, that tells us we don't have missing completely at random. But we'll never know for sure that we don't have missing total at random, because part of missing total at random, it's kind of an ideal pie in the sky goal, because the only way we could truly know it is if we actually had access to all unobserved variables, which of course we don't. So generally what we're aiming for in our methodological setup, so before we ever run our study, we want to ask, is there any way people would miss providing data? Is there any way that people would maybe miss filling out a survey? Is there any way that, this study requires people to come in at various times and some people just aren't going to make it? If that's going to occur, can I design the study to aim for missing completely at random, to try to make sure that it doesn't become a systematic problem? What we're usually going to be able to test for is something different, and that is missing at random. So the data are related to other observed variables. However, the missing data is not a function of the variables for which the data is missing. Did not take a measure for some reason not related to the treatment or outcome. So for example, we might find that women were more likely to fill out the survey completely and men were a little less likely, but our study actually isn't focused on gender. That would be an example of missing at random. So yes, we know there's a systematic predictor of whether or not you missed a particular item or a particular survey, but it's not relevant necessarily to what we're actually examining. Now again, that's a judgment call. That's based on the study that you've designed. It's based on past theory. Missing not at random is what we want to avoid, and if we do this, if we have missing not at random, we've violated an assumption. The data is systematically missing and is a function of the variable with missing data. Participants fail to respond because they're not comfortable with the questions, do not take the measure for reasonable reasons related to the measure. So for example, you might have what you're looking for are people that are involved with illegal narcotics. And everyone that is not involved in illegal narcotics filled out every one of your surveys. But anyone that admitted that they had taken illegal narcotics actually were likely to not fill out various personal details, were likely to not fill out actual information about where and when they were doing it. Now you've got missing not at random. The actual variables you care about are what's actually predicting whether or not someone actually responded or not. And we often find this in studies where we're really focused on quote-unquote illegal behaviors or kind of socially unaccepted behaviors. A lot of people will respond honestly if they have quote-unquote nothing to hide, are much less likely to respond honestly if they do have quote-unquote something to hide. So again, this isn't something that's easily tested just with statistics, but it is something we want to think about when we're designing our studies, and it's something that we do want to look for as a potential violation of the assumptions. And again, we can run statistics on data that's missing not at random, but we can't trust the inferences anymore, and that's what I really want to focus on. So hopefully this was an informative lecture, kind of got you to be thinking of the big picture of multivariate statistics and ready to start to dive in. Though I am out of town this week, I am available on email, so if you have any questions, feel free to email me, and I will see you next week.